Polar coordinates. Polar versus rectangular coordinates. Rectangular coordinates are the usual x-y coordinates that we use to describe positions of points in the plane relative to two perpendicular axes. Notice that a given point lies at the intersection of a vertical line along which x is constant and a horizontal line along which y is constant. Alternatively, a given point also lies at the intersection of a line through the origin and a circle centered at the origin. So we can associate each point in the plane with the radius r of that circle and the measure of the angle theta between the positive x-axis and the line through the point in the origin. So to each point in the plane we can assign a radius r and an angle theta, and we may label the point xy alternatively as r, theta. Here we use double parentheses to distinguish polar from rectangular coordinates. This notation is not standard. The relationships between rectangular coordinates and polar coordinates are as follows. X is equal to r times cosine theta, and y is equal to r sine theta, which allows easy conversion from polar to rectangular coordinates. Also, r squared is equal to x squared plus y squared, and tangent theta is equal to y over x, which allow conversion from rectangular to polar coordinates. For instance, the point with rectangular coordinates 1, 1 has distance square root of 2 from the origin and forms an angle of pi over 4 with the positive x-axis. So we may label the point with polar coordinates square root of 2, pi over 4. On the other hand, we could use instead a different coterminal angle, such as negative 7 pi over 4, and label the point as square root of 2, negative 7 pi over 4. So we see that, in at least one sense, polar coordinates are not unique. To see a different sense in which different representations occur, consider the point with rectangular coordinates 0, 2. The simplest description of this point in polar coordinates is 2, pi over 2. On the other hand, we can associate with this point the angle minus pi over 2 together with a radius of negative 2. So minus 2, minus pi over 2 is an equivalent description of this point. Thus radii can be negative. Any point other than the origin can be described with either a positive or a negative radius. A good way to think of this is to imagine that at any angle theta there is a copy of the real number line whose positive end corresponds to the terminal side of the angle theta and whose negative end points in the opposite direction. This is a polar grid. Circles centered at the origin correspond to fixed values of r, and lines through the origin correspond to fixed values of theta. Let's assume that the darker circles here have radii 1, 2, 3, and 4, and let's plot and label a few points. This point can be associated with a radius of 3 and the angle pi over 6, so we label the point 3, pi over 6. This point can be associated with a radius of 2 and the angle 2/3 pi, so we label the point 2, 2/3 pi. For this point, we can use a radius of 1 and the angle pi, so we label the point 1, pi. Here we can use a radius of 4 with the angle 5 pi over 4. For this point on the negative y-axis, we can use a radius of 3 and the angle 3/2 pi. Now let's replace the polar grid with a rectangular grid and find the rectangular coordinates of each of these points. Recall the formulas x equals r cosine theta and y equals r sine theta. The point with polar coordinates 3, pi over 6 has x coordinate 3 cosine pi over 6 and y coordinate 3 sine pi over 6, so the rectangular coordinates are 3 times the square root of 3 over 2, 3/2. The point with polar coordinates 2, 2/3 pi has x coordinate 2 times cosine of 2/3 pi and y coordinate 2 times sine of 2/3 pi, so the rectangular coordinates are -1, square root of 3. The point with polar coordinates 1, pi obviously has rectangular coordinates -1, 0. The point with polar coordinates 4, 5 pi over 4 is -2 root 2, -2 root 2 in rectangular coordinates. And 3, 3 pi over 2 in polar coordinates is 0, -3 in rectangular coordinates. Now let's label a few points with rectangular coordinates and then find their polar coordinates. We'll look at 2, 0, 3, 2, -1, 3, -4, 0, -1, -1, and 1, -2. Here's a polar grid. Now let's recall the formulas r squared equals x squared plus y squared and tangent theta equals y divided by x. The point with rectangular coordinates 2, 0 may be labeled with radius r equals 2 and angle theta equals 0. So the polar coordinates are also 2, 0. The point with rectangular coordinates 3, 2 may be labeled with radius r equal to the square root of 3 squared plus 2 squared equals the square root of 13, and angle theta equal to the inverse tangent of 2/3. The point with rectangular coordinates -1, 3 may be labeled with radius r equal to the square root of 1 squared plus 3 squared, or the square root of 10. The inverse tangent of 3 divided by -1 is a negative fourth quadrant angle, so the angle here is the inverse tangent of -3 plus pi. Since the inverse tangent is an odd function, we can rewrite that as pi minus the inverse tangent of +3. The point -4, 0 can be labeled with r equals 4 and theta equals pi. The point -1, -1 has polar coordinates r equal to the square root of 2 and theta equal to 5 pi over 4. The point 1, -2 has polar coordinates r equal to the square root of 5 and theta equal to the inverse tangent of -2, which is the negative angle shown here. Polar equations and graphs. A circle centered at the origin has a very simple polar equation. R equals capital R, where capital R is the radius of the circle. Note that each point on the circle has unique polar coordinates r, theta if theta is restricted to the half open interval from 0 to 2 pi, or any other half open interval of length 2 pi. Note also that circles centered at the origin, which correspond to constant values of the polar coordinate r, are polar grid curves or coordinate curves. By restricting the angle theta to shorter intervals, we can describe various parts of the circle. For instance, the top half of the circle here is described by r equals capital R for theta between 0 and pi. Lines through the origin have polar equations that are just as simple. Every point on such a line may be associated with the same angle, theta naught. So an equation of the line is simply theta equals theta naught, and the entire line is obtained as r ranges from -infinity to infinity. These are also grid curves or coordinate curves since they correspond to constant values of the second polar coordinate theta. Just as we can describe a part of the circle r equals capital R by restricting the free variable theta, we can also describe a segment on a line theta equals theta naught by restricting the free variable r. Here you see the result of restricting r to the closed interval from -1 to 1. Circles through the origin. Let's start with an example. Convert the equation r equals 2 cosine theta to rectangular coordinates in order to identify its graph. The key here is to realize that multiplying each side of the equation by r will make the right side 2r cosine theta, which is 2 times x. Also, the left side becomes r squared, which is x squared plus y squared. So we have x squared plus y squared equals 2x. This is the equation of a circle. To find the center and radius of the circle, we'll subtract 2x from both sides, and then complete the square on the x terms by adding 1 to both sides. So we have x minus 1 squared plus y squared equals 1, which tells us that the graph is the circle centered at 1, 0, with radius 1. So let's plot the graph of the polar equation to see how the circle is traced out. It is helpful to look simultaneously at the graph of r versus theta as rectangular coordinates. There we have a simple cosine wave with amplitude 2. From that graph, we see that r equals 2 when theta equals 0, so we begin by plotting the point with polar coordinates 2, 0. Now, as theta increases from 0 to pi over 6, r decreases from 2 to the square root of 3. As theta increases further to pi over 3, r decreases to 1. And when theta equals pi over 2, r equals 0, and so the polar curve approaches the origin tangent to the y-axis, which is the line theta equals pi over 2. For theta between pi over 2 and 3 pi over 2, we will have negative values of r. At theta equals 2/3 pi, the radius is minus 1. At theta equals 5 pi over 6, the radius is minus the square root of 3, and the circle is completed when theta equals pi, for which r is minus 2. So the circle is completely traced out as theta goes from 0 to pi. For theta between pi and 3/2 pi, the top half is traced out again, this time with negative radii, and for theta between 3/2 pi and 2 pi, the bottom half is traced out again, this time with positive radii. In exactly the same manner as in the previous example, conversion of the equation r equals 2 R cosine theta to rectangular coordinates results in the rectangular equation of the circle centered at R, 0 with radius absolute value of R. Rotation. Rotation of a polar graph about the origin through an angle alpha results in the graph of the same equation with theta replaced by theta minus alpha. This is analogous to a horizontal shift in rectangular coordinates. Here, rotation through an angle alpha results in the graph of r equals 2 times R times cosine of theta minus alpha. It's easy to see that the center of the rotated circle will have polar coordinates R, alpha, and therefore it has rectangular coordinates R cosine alpha, R sine alpha. Now let's rewrite cosine of theta minus alpha using the difference formula for cosine. This gives r equal to 2 R cosine theta times cosine alpha plus sine theta times sine alpha. Notice that this equals 2 times the x-coordinate of the circle's center times cosine theta plus 2 times the y-coordinate of the circle's center times sine theta. So, for an equation of the form r equals a cosine theta plus b sine theta, the center of the circle can be easily identified from the coefficients a and b. That is, the graph of r equals a cosine theta plus b sine theta is a circle with center a over 2, b over 2. And since we know that the circle goes through the origin, the radius of the circle is the distance from the origin to a over 2, b over 2, which is R equals 1/2 of the square root of a squared plus b squared. Also, the circle is traced out twice as theta goes from 0 to 2 pi. Let's assume that R equals 1 in the figure. Now, for instance, consider rotation through an angle of pi over 4. The center is now at root 2 over root 2, root 2 over root 2. And so the polar equation is r equal to the square root of 2 times cosine theta plus the square root of 2 times sine theta. If we rotate through an angle of pi over 2, the center is now at 0, 1. So the polar equation is r equals 2 sine theta. Rotation through pi radians puts the center at minus 1, 0, and the polar equation becomes r equal to minus 2 cosine theta. Rotation through 3 pi over 2 radians puts the center at 0, minus 1, and so the polar equation becomes r equals minus 2 sine theta. Limicons and cardioids. Let's begin here with an example. We'll plot the graph of the polar equation r equals 1 minus 2 cosine theta. This equation is typical of equations in which r equals a constant plus a multiple of cosine theta or sine theta. First, we'll plot the graph of r versus theta as rectangular coordinates, and we'll make a table of values of theta and the corresponding r. When theta equals 0, r is equal to minus 1. So we start by plotting the point with polar coordinates minus 1, 0. When theta equals pi over 6, r is equal to 1 minus the square root of 3, which is between minus 1 and 0. So as theta goes from 0 to pi over 6, points on the graph move closer to the origin. When theta equals pi over 3, r is equal to 0. So the graph arrives at the origin tangent to the line theta equals pi over 3. Now, for theta between pi over 3 and 5 pi over 3, r will be positive. When theta equals pi over 2, r equals 1. So as theta goes from pi over 3 to pi over 2, points on the graph move away from the origin, arriving at the y-axis at the point where y equals 1. When theta equals pi, r equals 3. So as theta goes from pi over 2 to pi, points on the graph move farther away from the origin, arriving at the x-axis at the point where x equals minus 3. At theta equals pi, r begins to decrease. When theta equals 5 pi over 4, r equals 1 plus the square root of 2. And when theta equals 3 pi over 2, r is equal to 1. So the graph will cross the y-axis at the point where y equals minus 1. When theta equals 5 pi over 3, r is again 0. So the graph arrives at the origin tangent to the line theta equals 5 pi over 3. For theta between 5 pi over 3 and 2 pi, r will again be negative. At theta equals 11 pi over 6, r equals 1 minus the square root of 3. And at theta equals 2 pi, r equals minus 1. And so the graph ends up where it began. This figure is an example of a limacon. Notice the inner loop, which was traced out while r was negative. More limacons. Let's plot the polar equation r equals 3 minus 2 cosine theta. Notice that this is similar to the previous equation, except here the coefficient of cosine theta is smaller than the constant term. As a result, r will always be positive. Here are the rectangular graph of r versus theta and the polar graph, which is a limacon without the inner loop. Now let's watch as the polar curve is traced out as theta goes from 0 to 2 pi. Once again. Next, let's plot the polar equation 1 minus cosine theta. Notice that this is similar to the previous equations, except here the absolute value of the coefficient of cosine theta is equal to the constant term. As a result, r will always be non-negative and will equal 0 when theta equals 0 or 2 pi. Here are the rectangular and polar graphs. This special case of a limacon is called a cardioid because of its heart-like shape. Now let's watch as the polar curve is traced out as theta goes from 0 to 2 pi. And once again. The graph of 1 plus cosine theta is also a cardioid. In fact, it's a rotation of the previous one through pi radians, since cosine of theta minus pi equals minus cosine theta. Now let's watch as the polar curve is traced out as theta goes from 0 to 2 pi. The graph of 1 minus sine theta is also a cardioid. In fact, it's a rotation of the first one through pi over 2 radians, since cosine of theta minus pi over 2 equals sine theta. Now let's watch as the polar curve is traced out. Roses. Consider the equation r equals sine of 2 theta. Its polar graph is called a four-leaf rose. Let's see how this polar graph is traced out as theta goes from 0 to 2 pi. Notice that 2 leaves correspond to positive radii and 2 leaves correspond to negative radii. The graph of r equals cosine 2 theta will be the same figure rotated through minus pi over 4 radians, since the sine of 2 times theta plus pi over 4 equals sine of 2 theta plus pi over 2, and that equals cosine of 2 theta. Let's watch as this polar graph is traced out. Now let's look at r equals sine of 3 theta. Its polar graph is a 3-leaved rose. Notice that as theta goes from 0 to 2 pi, the figure is traced out twice. The polar graph of r equals sine of 4 theta is an 8-leaved rose. So we've seen so far that when the coefficient of theta inside the sine function is even, the number of leaves in the figure is twice that number. On the other hand, the graph of r equals sine of 3 theta had 3 leaves, and we'll see next that the graph of r equals sine of 5 theta has 5 leaves. And, just as with r equals sine of 3 theta, the rose is traced out twice as theta goes from 0 to 2 pi. In fact, it is true that the graph of r equals sine of n theta, or r equals cosine n theta, is an n-leaved rose if n is odd, and a 2n-leaved rose if n is even. Example: find the polar equation that is satisfied by all points whose distances from -1, 0 and 1, 0 are reciprocals, and plot its graph. We'll start with the equation in rectangular coordinates. The distance from xy to -1, 0 is the square root of x plus 1 squared plus y squared, which we set equal to the reciprocal of the distance from xy to 1, 0, which is 1 over the square root of x minus 1 squared plus y squared. Now let's square both sides and multiply both sides by x minus 1 squared plus y squared. This gives us x plus 1 squared plus y squared all times x minus 1 squared plus y squared equals 1. Now expanding the products x plus and minus 1 squared gives us x squared plus 2x plus 1 plus y squared times x squared minus 2x plus 1 plus y squared equals 1. Now let's replace x squared plus y squared with r squared and replace 2x with 2r cosine theta in each of the factors on the left. So we now have a polar equation which needs to be simplified. Notice that the product here has the form of a plus b times a minus b, where a equals r squared plus 1 and b equals 2r cosine theta. So the expanded product will be a squared minus b squared, or the square of r squared plus 1 minus 4r squared cosine squared theta. When we multiply out the first term here, we'll have r to the fourth plus 2r squared plus 1, and after subtracting 1 from both sides, that will be just r to the fourth plus 2r squared. So the equation then becomes r to the fourth plus 2r squared minus 4r squared cosine squared theta equals 0. Now let's divide both sides by r squared and write the equation as r squared equals 4 times cosine squared theta minus 2, or r squared equals 2 times 2 cosine squared theta minus 1. Now 2 cosine squared theta minus 1 turns out to be the same as cosine of 2 theta by the double angle formula for cosine, an identity that may be more familiar if we rewrite 2 cosine squared theta minus 1 as cosine squared theta minus sine squared theta. Regardless, we now have our final form for the polar equation. R squared equals 2 times cosine 2 theta, which is equivalent to r equal to plus and minus the square root of 2 times cosine of 2 theta. Now let's plot the graph. It turns out that the graph of r versus theta as rectangular coordinates looks like this. To see why this graph appears as it does, compare it to the graph of 2 times cosine of 2 theta, shown here in red. Notice that wherever 2 cosine 2 theta is positive, there are 2 points on the black graph with y-coordinates plus and minus the square root of 2 cosine 2 theta. And notice the gaps corresponding to those values of theta where 2 cosine 2 theta is negative. Now let's plot the polar curve. Corresponding to theta equals 0, we have r equals plus and minus the square root of 2, so we plot 2 points at plus and minus the square root of 2 on the x-axis. When theta equals pi over 12, we have r equals plus and minus the square root of 2 cosine pi over 6, which equal plus and minus the square root of the square root of 3, or plus and minus the fourth root of 3. Those are roughly plus or minus 1.3, so we plot 2 points somewhat closer to the origin on the line theta equals pi over 12. When theta equals pi over 6, we have r equals plus and minus the square root of 2 cosine of pi over 3, which equal plus and minus 1. So we plot 2 points at distance 1 from the origin on the line theta equals pi over 6. Now notice that r squared decreases to 0 as theta increases to pi over 4. So both parts of the curve we have so far will meet at the origin when theta equals pi over 4. No part of the graph corresponds to theta between pi over 4 and 3 pi over 4, since 2 cosine 2 theta is negative there. At theta equals 3 pi over 4, r squared equals 0, and for theta between 3 pi over 4 and pi, we continue plotting pairs of points, completing the figure as seen here. For theta between pi and 2 pi, we would simply retrace the same figure again. This is a curve known as a lemniscate. To illustrate the geometric definition, which says that for any point on the curve, the distance to minus 1, 0 and 1, 0 are reciprocals, let's plot a circle with radius 1/2 centered at 1, 0, and a circle with radius 2 centered at minus 1, 0. Notice that those circles intersect the lemniscate at the same points. This would be true for any such circles whose radii are reciprocals, provided they intersect the lemniscate at all. The slope of the tangent line. Suppose that we have an equation of the form r equals f of theta. The chain rule tells us that the derivative of y with respect to x times the derivative of x with respect to theta will be equal to the derivative of y with respect to theta. Therefore, the derivative of y with respect to x is equal to the derivative of y with respect to theta divided by the derivative of x with respect to theta. So let's now calculate those derivatives of x and y with respect to theta. X is equal to r cosine theta, or f of theta times cosine theta. Therefore, by the product rule, dx d theta will be equal to f prime of theta times cosine theta plus f of theta times minus sine theta. Y is equal to r sine theta, or f of theta sine theta, and so dy d theta, again by the chain rule, will equal f prime of theta times sine theta plus f of theta times cosine theta. So these are the denominator and the numerator of the derivative of y with respect to x, respectively. Now, for instance, if we're interested in finding horizontal tangents, we would set dy dx equal to 0, and dy dx would equal 0 only if the numerator of the quotient equals 0, and that's when dy d theta is equal to 0, provided, of course, that the denominator dx d theta is not also 0. We can locate vertical tangents by looking for where dy dx is undefined. And that's going to happen when the denominator dx d theta equals 0, while the numerator dy d theta is not 0. Example. Find the slope of the graph of r equals 1 plus 2 sine theta at the points plus and minus 1, 0. Let's first look at the graph of the equation. It's a limison with an inner loop, and it's symmetric about the y-axis. The 2 points we're concerned with are shown here in red. And here are the tangent lines at those 2 points. Note that by symmetry, the slopes will be negatives of each other. Also, the point 1, 0 corresponds to theta equals 0, and the point minus 1, 0 corresponds to theta equals pi. Recall that dy dx equals dy d theta divided by dx d theta. So let's compute the derivatives of x and y with respect to theta. Since x equals r cosine theta, and r equals 1 plus 2 sine theta, we have x equal to 1 plus 2 sine theta times cosine theta. And since y equals r sine theta, we have y equals 1 plus 2 sine theta times sine theta. Now using the product rule, we have dx d theta equal to 2 times cosine theta times cosine theta plus 1 plus 2 sine theta times minus sine theta. And simplification gives us 2 times cosine squared theta minus sine squared theta minus sine theta. Similarly, dy d theta equals 2 cosine theta times sine theta plus 1 plus 2 sine theta times cosine theta, which simplifies to cosine theta times 4 sine theta plus 1. So we write dy dx by putting dx d theta in the denominator and dy d theta in the numerator. Now let's evaluate dy dx at theta equals 0. We get 1 times 0 plus 1 in the numerator, and 2 times 1 minus 0 in the denominator, which simplifies to 1/2. Now let's evaluate dy dx at theta equals pi. We get minus 1 times 0 plus 1 divided by 2 times 1 minus 0, which equals minus 1/2, as expected by symmetry. One more example. Let's find the rectangular coordinates of the points on the limicon r equals 7 plus 15 cosine theta, where the tangent line is horizontal. So again, we're dealing with a limicon. This one is symmetric about the x-axis. Here are two of the points we're looking for. These have the same x-coordinates, and their y-coordinates are negatives of each other. There are also 2 points on the inner loop where the tangent line is horizontal. Again, those have the same x-coordinates, and their y-coordinates are negatives of each other. The red point at the top of the limicon will correspond to a first quadrant angle theta and a positive radius r. The red point at the bottom will correspond to a fourth quadrant angle theta and a positive radius r. The blue point at the bottom of the inner loop will correspond to a second quadrant angle theta and a negative radius r. The blue point at the top of the inner loop will correspond to a third quadrant angle theta and also a negative radius r. To find these points, we first need to compute dy d theta, since dy d theta will equal 0 at each of them. We begin by writing y equals r sine theta, with r equal to 7 plus 15 cosine theta. Now by the product rule, dy d theta will equal minus 15 sine theta times sine theta plus 7 plus 15 cosine theta times cosine theta, which equals minus 15 sine squared theta plus 15 cosine squared theta plus 7 cosine theta. And since we want to set this equal to 0 and solve, we'd like for it to be in terms of cosine only. So let's replace sine squared theta with 1 minus cosine squared theta. And now we have a quadratic expression in cosine theta. So by the quadratic formula, dy d theta equals 0 when cosine theta equals minus 7 plus or minus the square root of 7 squared minus 4 times 30 times minus 15, all divided by 2 times 30. The quantity under the radical is 1,849, whose square root turns out to be 43. So the two numbers we have are 36 over 60 and minus 50 over 60, which simplify to 3/5 and minus 5/6. So at each of our 4 points, cosine of theta equals either 3/5 or minus 5/6. Knowing cosine theta is enough to calculate the corresponding r from the formula 7 plus 15 cosine theta. When cosine theta equals 3/5, we have 7 plus 15 times 3/5, and when cosine theta equals minus 5/6, we have 7 plus 15 times minus 5/6. These equal 16 and minus 11 halves, with 16 corresponding to cosine theta equals 3/5 and minus 11 halves corresponding to cosine theta equals minus 5/6. Now we can easily compute x-coordinates from the formula x equals r cosine theta. And we can compute y-coordinates from y equals r times plus or minus the square root of 1 minus cosine squared theta. With r equals 16 and theta equals 3/5, we get x equal to 48 over 5. This is the x-coordinate of both of the red points in the figure. The corresponding y-coordinates are plus or minus 16 times the square root of 1 minus 3/5 squared, which turn out to be plus or minus 64/5. With r equals minus 11 halves and cosine theta equals minus 5/6, we get x equal to 55 over 12. This is the x-coordinate of both of the blue points in the figure. The corresponding y-coordinates are plus or minus 11 halves times the square root of 1 minus the square of 5/6, which turns out to be plus or minus 11 halves times the square root of 11 divided by 6, or plus or minus 11 root 11 divided by 12.